Anyway, good morning, everybody. We let the technical people solve the problem. And I'm really excited to be here because it's, I think, the first time after 2 years that I'm talking to such an audience. Everything until now was done by Zoom or by an amazing social distancing where people could not interact with one another. And so for me, it's also a kind of a personal celebration. So I changed a little bit the topic because the audience is a little bit different than I thought it's going to be. And I will talk about a general subject, and that's the direction where medicine is going today. But I will nevertheless relate it to the COVID-19 pandemic when I'm going to talk about bioethical issues that are related to the revolution that medicine is undergoing these days. So you see here the beautiful city of Haifa. The medical school is here. My laboratory is on the 11th floor, looking to the sea. Just a wonderful place to be. So, everybody wants to live forever, to live long, right? We are, and we want to remain beautiful and young. And on top of it, mostly we want to remain healthy. So we want to live long in high quality of life. So let's discuss historically what's behind this will. There is something behind it. It's not only our will, but let's examine what history tells us. So 120 years ago, at the turn of the 20th century, people lived almost all over the world about 50 to 55 years. This was the average time span. About nearly 120 years ago, people died of infections. There was no antibiotics. We'll talk about antibiotics development in a short while. There was no imaging. Röntgen, Wilhelm Conrad Röntgen, the German scientist, the first Nobel Prize in physics in 1901, just came out with his invention, and it took several years to really implement it into hospitals. There were no vaccines at all. We were not vaccinated. And there were lots of wars. People got infected, farming, tetanus, and so on and so forth. Women died in delivery because of bleeding. We didn't know anything about blood types. We couldn't even transfuse blood. Think just merely 120 years ago. We knew basically almost nothing about medicine and about biology. So the lifespan was, as I said, about 50 to 55 years. There were big families. People had like families of 5, 10 children because many of them died during childhood, and they needed workforce to help the family in farming, in doing physical work, and so on and so forth. And in one century, the 20th century, the lifespan was extended by more than 30 years. So now we are living in the Western world about, on the average, 80, 85 years, women a little bit more, men a little bit less, but we extended lifespan by more than 30 years. This is really a miracle. And if we look back into the history, to old history, to Egyptian history, Greek history, and even Chinese history, as much as we have access to, about 4,000 years ago, the mummies that we are finding in the pyramids in Egypt, they died on the average at the age of 25 to 30 years. This was the lifespan 4,000 years ago. So it took about 4,000 years to bring life from 30 to 50, merely 20 years, and merely 100 years, about 2.5% of the time, to go with 30 more years. So really something fundamental did happen in the 20th century. And this something fundamental is not secret, it's all science and technology. It's antibiotics and vaccination and clean water and sewage system and understanding diet and hospitals and development of medicine and so on and so forth. Altogether, these factors accumulated in order to give us 30, 35 more years. Now, an interesting question is whether the trend is going to continue. Are we going to add another 30 or 40 or 50 years in the current century, in the 21st century? Well, people think that this is not going to be the case. We are starting to plateau. And the plateau, the prediction is, it's only a prediction because nobody really knows, appears to be at around 115 and 120. So we still have another 35 years to go, but we are moving slowly. And why we are going to die? Again, everything is not clear, because as we are analyzing the perspective, new technologies are coming. So there are burden of mutations, of course, that burdening us. It's mostly quality control. The issue is quality control. Our inability, for example, to remove aberrant proteins, oncoproteins that cause cancer, aggregated proteins in the brain. The system that we discovered, on which I'm not going to talk, the ubiquitin system, is involved among its many other functions in quality control, in removal of aberrated and aggregated, mutated, misfolded proteins. But nevertheless, biological systems have their own lifespan. They collapse. The immune system collapsed. We just seen it in the COVID-19 pandemic, that it mostly affected old people with compromised immune system. And young people, most of them went through it rather lightly. So it's a kind of collapse of all the systems, but nevertheless, it's still a wonder. Think about a human being that lives for 80 years. 80 years. So day and night, we are breathing, we are taking oxygen, we are expiring carbon dioxide. The heart is beating 60 times a minute, night and day, Saturday, holiday, Christmas, Jewish holiday, doesn't matter. The biology is completely indifferent to all the ceremonies that people invented for themselves to enjoy life. And it's an amazing machine. There is no other machine like the organism, the living organism, and in particular the human organism. Think about the most expensive car you might think of. Think about, I don't know, an ultra expensive Mercedes. How much it lives? Nothing. It drives, what, 2 hours a day, 3 hours a day at the most, times probably Saturday the people are resting. So it's about 20 hours a week, so it's 80 hours a month. So it's 1,000 hours a year. And let's say that it lives for 10 years even, so 10,000 hours. 10,000 hours, how much it's in human life? It's about 15 months, approximately, more or less. So think about a baby that is 15 months. It cannot speak, it cannot walk, it cannot do anything. So the best car, and during that time it rests a lot, and in the night and in the weekend, it go to the machine shop several times. So the efficiency of the organismal machine is really unbelievable. It's unprecedented. There is nothing like that is man-made. We cannot imitate the ability of nature. But nevertheless, it's coming to an end. So, cure for all diseases. Of course, we have made huge advances in recent years, but most of the advances are what I call in diseases that have to do with the pipelines of the body, with the installation. So we are able to replace joints, for example, to put titanium joints in the shoulder, in the hip, in the knee. We are able to change the vascular system partially. We are able to put, let's say that in the main conduit of the blood, the aorta, we are able to replace it with a modern vascular system if it's degenerated. We are still fighting very hard in diseases in which the mechanism is awfully complicated. Take, for example, cancer. We have made great advances in cancer, but the disease, we are going to talk about it, is still fooling us because of the genome instability. You know, if we are treating one mutation, another mutation appears under pressure. We are losing what we call the genome stability. We might talk about it later. I don't want during my talk to go too much and too deep into technological jargon. So cancer is still a major problem, and it's #1 killer in many of the developed countries, including in my own country. Brain diseases, we are really far away from all brain diseases, though from Alzheimer and Parkinson, all the diseases that are leading to two main syndromes. One syndrome is, of course, movement disorders, like Parkinson's disease, and so on, that we are losing our stability. And the other one is, of course, cognitive deterioration. We are really losing our memory. We are losing ourselves in a way. You know, what you are seeing at the end of the process, you are seeing a shell of a person. I mean, the person looks like the person used to look like, but there is nothing left inside. Really nothing left inside. So those are diseases in which we understand very little. We start to get a kind of a clue, but we are far away from being there. There are even doubts in the community whether what we thought for years is the reason for these diseases, which I mentioned initially, aggregated proteins in the brain, is indeed the reason, because people tried numerous ways to get rid of these aggregated proteins, and nonetheless, they didn't advance any therapeutic approach to these diseases. So there is currently a big discussion in the community of whether at all we understand even the reason, not talking about developing therapies. So we are making an advance, no doubt, but we are still far away. So let's talk about where medicine is going these days. And if we are looking from 30,000 feet, I think that medicine is going in three main directions. One direction is, of course, engineering, classical engineering, bolts and nuts, artificial valves. We are not successful in making an artificial heart. There is a heart-lung machine, but it's only transient for operation when we have to stop the circulation. But we cannot replace a heart with an artificial heart. This was a colossal failure that has been with us for 50 years, since the original artificial heart of Cole from Utah. But artificial valves, yes, to the different arteries and inside the heart. So this is going on, as I mentioned, artificial joint and so on and so forth. But also the technology is also going to mini cameras. We are able to put a camera, to swallow a little camera, and after 3 days it's coming in the stools and it takes pictures of all your intestine in case there are polyps or some pathological processes that we can diagnose. The imaging technology has developed immensely. Röntgen, X-ray have been living with us for 80 years, from the early 1920s all the way to the 1980s. Myself, as a medical student, I grew on X-ray, but all of a sudden, CT scan came, and MRI came, and functional MRI came, and methodologies with much better resolution that can look into soft tissues came out, and they are even dynamic, so we can do a lot of intervention under imaging. We can replace, the valve replacement is done under imaging, of course, and we don't need any operation. We can introduce the folded valve via a tube into the artery. It doesn't require anything. The physician sees it in the imaging system, and then it opens it up, and it sits in the right place. So imaging has become not only very useful to view things, but also to intervene in pathological processes. We call it interventional imaging. So that's all engineering. Surgery is being done now. I'm a surgeon by training, and I was operating like in a butcher shop. I mean, we were cutting. Now there are much better machines to cut, the robots. They are cutting much more gently. There is the famous Da Vinci, and it was really became, initially it was generated only for prostate operations, but now it's being used almost across the board in surgery, for abdominal operation, for brain operation, and basically it's joysticking. The surgeon is sitting on a chair near the joystick, and the arm, which is extremely stable and extremely gentle, can do the operation. It's the morbidity rate and the death rate, mortality rate after those operations is much, much lower than it used to be just a few years ago when operations were still manual. So this is another engineering. It's pure engineering, of course, sophisticated engineering that is associated and deeply associated to computer sciences and imaging and so on and so forth. The other direction that medicine is going is what we call molecular engineering, or we call it engineering, but it's not the classical engineering. Of course, our trial to change the function of tissues. For example, I bring you one example is diabetes. This is really a pandemic or epidemic, however you want to call it. Millions and millions of people worldwide are getting diabetes, partially by genetics, partially because of behavior, mostly obesity, and so on and so forth. And in diabetes, a hormone is missing called insulin, and the insulin role is to introduce glucose, the sugar, the energy source, into the cells. And if there is no insulin, people are basically drowning in an ocean of sugar. You say, I have high sugar, but the sugar is useless because it's circulating in the blood and get nowhere. And this is not the problem. The sugar is not the problem because the body can find other sources for energy like fat and proteins. The issue are the complications of the disease, mostly vascular complication. People become blind. The blood flow to the kidney goes down and they suffer from kidney insufficiency. Blood flow to the limbs becomes limited and they are undergoing amputations. Actually, you can see typically that the legs are being amputated like a salami. You know, you take one piece and then the disease progresses and then you take another piece and another piece. So it's an awful disease, a really debilitating disease. And what people are trying to do is to take cells, either embryonic cells or cells from the patient, and to re-engineer them, the DNA, in order that it will secrete insulin, but not only secrete insulin, but secrete insulin in response to glucose. So when we eat and have a lot of sugar in the blood, we want high insulin, so it will go into the cell to serve as a source of energy. But if we are not eating and there is no need in insulin, the cells should be sensitive and lower the secretion of insulin, so we shall not run into sub-levels, into low levels of sugar, because the brain is the only organ in the body that is not dependent on insulin. The brain uses sugar all the time, and if the sugar level goes down, there is no sugar for the brain, and we are suffering from severe neurological syndrome. So we need not only to put the DNA for insulin, but also to make the secreting cells sensitive to glucose. So this is one example for what we call genetic engineering, and there are many other diseases in which we are trying it. And genetic engineering is going further, and when we shall talk on CRISPR and other technology to repair genes, we shall go back to this vastly important novel technology. And the third direction that medicine is going, besides these two types of engineering, is of course drugs. You go to the pharmacy and you buy a drug, but the drug didn't start its way in the pharmacy. It started its way long before in the laboratory, typically in either a university laboratory of an individual researcher or in a pharmaceutical company. Took a long time and huge amount of money in order to bring it to the pharmacy, because we have to try that it's indeed efficient. We need to learn the side effects, and it's billions of dollars. Actually, the average development of current drug, I'm not talking about COVID-19 vaccine because these are exceptions, and I'll tell you in a minute why it's an exception, but a novel drug that's coming from scratch, the development price is between 5 to 10 billion, 10 to the $9. COVID-19 is an exception. It also cost a lot, and there was a huge effort that was partially funded by the American government, but all the knowledge was there. So the knowledge came from the central dogma of biology, from the fact that we knew that information is flowing from DNA to RNA to proteins. What we need is a protein at the end. We need an antibody to neutralize the virus. But people realize that if we shall inject messenger RNA as one technology, the messenger RNA will go into the cells. Of course, they had to develop the technology, the nanolipid particles that will go into the cells, but once the messenger RNA is in the cell intact, it will go ahead and will be transcribed to a protein and generate, because it's a foreign protein, it generates the spike protein of the virus, then the immune system will jump on it and will generate antibodies and T cells for long time memory, and so on and so forth. So basically the people of Moderna and Pfizer used already a knowledge that has been there since the 50s or even the late 40s in order to make it, and they had to improve it technically, of course, to make the RNA less immune by changing some base, to pack it rightly, and so on and so forth. But these were all important, fundamentally important technical advances, but not, I would say, principal advances that have been there. So the development was much shorter. So, drugs. So now what I want to focus in the remaining part of my talk is about development of drugs. And we can look, again, it's my own view, because one of my hobbies is history, and especially history of medicine. So I kind of try to put it in a simple way. And we are going to talk about development of drugs in the current century, but in order to understand what brought us, we need to go a little back to the history. And the history is still the 20th century, so we are not going to old history. And the first revolution, the first, I would say, generation of drugs were incidental drugs. Drugs that were developed by serendipity. People didn't mean to develop them, but somehow they came out. And I'll bring you two brief examples. One example is, of course, aspirin. Aspirin was developed by Bayer AG. It's a German, huge German pharmaceutical company. And it was generated by two scientists. One of them is, you see them on the right side, Arthur Eichengrun. He was a Jewish, and of course his role in the development was somehow hidden and evaporated from the history, but people then dug back into it and put him in the right place. And the other one is Felix Hoffmann, that they were both working in Bayer. Felix Hoffmann's father was sick, and he developed rheumatoid arthritis. Rheumatoid arthritis is a disease of the joints in which the joint become inflamed, and basically it's a debilitating disease. You don't die on it, but you hardly live with it. So because it's very painful and you cannot move your joints, also of the foot, you hardly walk. You cannot do any simple movement. You cannot button your shirt. You cannot dry yourself after the shower. You cannot cut your food. You cannot, basically you are paralyzed. So they knew from old Egyptian literature, actually the drug it's not their drug. The drug was described 4,000 years ago by the old Egyptians, because the precursor of the drug is part of the ingredients in the willow bark leaves that grow on the banks of the Nile River. And the old Egyptian reported that once you are chewing the leaves, the taste is extremely bitter. It's hardly tolerable, but nevertheless, it has pain-relieving properties. So it took 4,000 years until these guys came and isolated the active ingredient from the willow bark leaves, and it was very bitter, and then they used the trick. They made some chemical chain. They acetylated it. I will not go into it. All in all, it's a very simple compound. You see it on the top. I shall not go into any chemistry. Everybody can synthesize it basically in the basement. Every first year chemical student, a student of chemistry, can synthesize it. It's an awfully simple compound. They changed it chemically, and it lost its bitterness, but it's kept its pain-relieving properties. And Felix decided to give it to his father, and lo and behold, not only the pain went away, but also the inflammation went away. So he recommended to Bayer to produce it, and Bayer indeed produced it initially as a powder, now as tablets. And aspirin became the most used drug in the history of the pharmaceutical industry. Most used, I mean, not by money coming to the company, but by tons, by weight. By weight. It's by far the most used drug ever been made. And gradually, especially in the last 30 years, it expanded its use in an unbelievable way. I'm one of the admirers of this drug. I've been using it for decades as a preventive drug, and I'll just tell you very briefly. There are still doubts about it, and there are many side effects, but nevertheless. So first of all, it's anti-inflammatory drug. And people discovered, I think that it was Paul Ehrlich, the German scientist, that chronic inflammation, he just described it without understanding the mechanism, leads at the end to cancer. So if you are suffering from chronic inflammation, especially in the bowel and in many other organs, you are at the end might succumb with high chance to cancer. So aspirin became not only anti-inflammatory, but also a cancer preventive drug. And for people who belong to a family that have high susceptibility for cancer, aspirin is highly recommended. Then people discovered that aspirin also can prevent the coagulation of blood. You know, blood coagulates when we get wounded. So they say, there is a disease, a very common disease in which the blood coagulates, and it's called the heart attack, right? In medical language, it's called myocardial infarction. And in heart attack, the arteries of the heart are coagulating. They develop precipitates of cholesterol. Here you can see the heart. You see the narrowing of the artery by the fatty precipitate of cholesterol. And in order to prevent, and this narrowing changes the turbulence of the blood, and the blood coagulates inside the artery. So people that suffered heart attack, the doctor will recommend them. Nowadays, it's not aspirin, it's another drug called Plavix, but I don't want to go into it. But aspirin became a kind of a preventive drug for a second heart attack. And so on and so forth. So you see that its use really was broadened enormously, and it became truly a magic drug. So this was, I'm going back, sorry. Another drug that was discovered by serendipity, a very famous drug, is of course penicillin. I will not talk about the importance of antibiotics, but in this case I just want to highlight how it was discovered. It was discovered by Alexander Fleming, who was a British microbiologist. And here you can see an agar dish. And what is an agar dish? An agar dish is a plastic dish, typically of diameter of 10 centimeters, on which bacteria are growing. You can grow bacteria. You see the schmear. The schmear are bacteria. And Fleming forgot the dish, one dish with bacteria on the table, and he forgot it opened. And he left for the weekend. When he came on Monday, he saw this white spot. And the white spot was, you know that the air is full of spores of fungi. A spore fell on the nutritious media and grew to form this colony of the fungi. But what Fleming noted, that there is a halo, you see, around it, that the bacteria cannot grow all the way to touch, all the way to the border of the colony. They are keeping a distance. And he came with an hypothesis. So this, I'm bringing this example in order to show you that success in science needs also very good eyes, very, very good eyes. And for sure, if I would have seen it in my lab, I would have thrown it away, the dish, as a contaminated dish. And he surmised that the bacteria, that the fungi, that the fungus is secreting a material that he called antibiotics, anti-against bio-life. And indeed, it took another almost 20 years to Sir Ernst Chain and Howard Florey to purify penicillin, which was the first antibiotic already used by the Allies during the invasion to Normandy, and saved the lives of thousands and thousands of soldiers during World War II. But then people realized that this colony belonged to the fungus, to the species Penicillium, but there might be other fungi that secrete different antibiotics. And Selman Waxman discovered streptomycin, which is secreted by Streptomyces, and so on and so forth. And the world has changed forever. So this is also discovery by serendipity. So now we move to the second revolution before we come to the last third one. And the second revolution is high throughput force screening of libraries. And this is a method that is being used today, nowadays, as we are moving to the next one. Peter, can I get water? You took all the water for yourself. What is it? So this is a marriage. This screening is a marriage between two technologies. We are just talking technologies all the time. Between two technologies. On one hand, chemistry has developed in a big way. Toda rabba. Thank you very much. Chemistry has developed in a big way, and organic chemist can synthesize virtually any compound, and thousands of compounds were synthesized for different purposes, drugs, industry, polymers, so on. But on the way to the synthesis, there are steps, step A, step B. So there are many intermediates. So people say, okay, let's take all the chemicals, arrange them in families, either by families of, that has something common in structure, or families that led to to synthesis of certain compounds. So they have now libraries. So this is the one pair of this wedding. The other pair is the ability of biologists to model diseases. And we are modeling diseases in the simplest way by cells. If you walk into my lab, you'll see big incubators, and cells are growing. And cells are coming from cancer patients, from neurological disease patients, from all kinds of patients. And we managed to eternalize them so they can grow forever. We even freeze them, and then we can thaw them and regrow them and so on. So people say, let's be matchmakers. Let's wed the two together. And the idea was to screen big libraries on a disease model. So let's say that you have a disease model of cancer, where cells are growing. So you take cancer cells, and you are screening one by one by one by one the million compounds that you have. Don't worry, you don't have to do it in your laboratory. If you walk into the big industry, you will see that it's all automated, helped by artificial intelligence. So there are robots that go into the incubator. They take at one time almost in a small dish, there are 400 wells. So in a little dish, there are 400 wells in which cells are growing, and it takes exactly 400 samples of these chemicals, put them on the cells, put the cells direct back into the incubator, come after a day, take the cells out, put them in the microscope. The microscope scans them automatically and say, it's all agreed, so you have a dish like that. So there are vertical rows and horizontal rows. You mark the vertical one with numbers, the horizontal one with letters, doesn't matter, and it tells you in well G11, the cells stopped growing. So it means that the drug that you put in can lead to arrest of cell growth. It's not a drug, it's a lead. And then you take it out and you do all kinds of toxicity experiments. You try it on different models, on models of tumors in cells, but at the end, out of many leads, probably one drug will come out. So this is brute force. You don't care about mechanism. You don't care about anything. You just assume that because the number of structure in nature is limited, one drug out of million will fit into the mutated protein that is the cause behind the disease and will inhibit its activity or will accelerate its activity if something is inhibited and so on and so forth. It's just based on statistical assumptions that turned out to be correct. And one drug that was developed based on it are statins. Statins are inhibitors of cholesterol biosynthesis. So they inhibit, I'm going back to cholesterol when we were talking about myocardial infarction, heart attack. Akira Endo, who worked in a pharmaceutical company in Japan, screened the library. In this case, it was a library of natural Japanese plant-originated compounds. So he generated a library of purified materials taken from plants, from fungi, from pine trees, from different, and he screened them in a model of a disease. It's not a disease. Cells that make high level of cholesterol. And he found that one of the compounds inhibits cholesterol biosynthesis. It inhibits the first enzyme in the pathway. And the company developed the first statin. Then it was sold to an American company. Doesn't matter the commercial route. And nowadays, millions of people worldwide are using statins. And it became now not the drug that is being sold by tons the most, but the drug that is making most of the money. It's now being competed by some anti-cancer drug. This drug was sold last year for $40 billion, $40 billion. By different companies, there are different versions of it, but it just shows you what it means. Amazingly, there are now programs that are using the power of computing, and I'm jumping now already to the third revolution, that you can take all the people that are using statins. Well, you don't have access to them, but in Israel, for example, we are a small country, basically the size of Hungary. We are 9 million people. So all the people in Israel are insured in two agencies, okay? So 6 million people are insured, health insurance, by one agency and 3 other million by another one. By the way, health insurance in Israel is mandatory by the law. It's not that you have to insure yourself. You are insured automatically, and part of your salary is being taken to health, and you are not asked. It's like income tax. So all of us are insured. So you can go and look at the files of 6 million people and ask who is taking statins. So you will find million people, let's say. And then you can ask, is there something peculiar about this million people beside the issue of the heart? Do they suffer more of prostate cancer? Are they more sensitive or less sensitive to psychiatric diseases? So you based on the knowledge of what happens in a big population, and you don't need to do any wet experiment. All what you need is to use databases. You can repurpose drug. You can use them for something that they were not meant to be initially. And indeed, it was discovered that statins have a positive effect on Alzheimer, and the population of Alzheimer patients is dropping due to, among those that take statins. Initially, it can be an artifact. It can be that these people that suffer from heart attack, a priori their genetics is so that they don't have Alzheimer. So it's still the responsibility of the investigator to find the causative linkage between statins and Alzheimer. And apparently there is one. It's not certain yet. It's still under investigation. But you see that the power of computing has entered into medicine in a big way. And there are many, and I'll show you. Well, I'm not going to show you because it's related to the ubiquitin system, but I might answer later on question, that there are many drugs that have been successfully repurposed for completely different disease to which they were designed a priori. So this is a drug that was based on screening. So now you may argue, okay, screening is good enough. If you have models for all diseases, then it's okay. Then you can screen all diseases. So here is the caveat. Well, we don't have good models to all diseases. For example, to psychiatric diseases, how cells can imitate psychiatric diseases, or even animals, behavioral studies. How can you measure depression or autistic spectrum, and so on and so forth. Second, remember that what we are doing, we are modeling even on a mouse. It's the same species of mouse that eats the same food, that is exposed to the same diet, the same food. In the morning, we turn the lights on in the cage. In the evening, we turn it. This is not the right model. And how did we come to this conclusion? And this conclusion is rather very new. It has been with us for only 20 years. The different people react differently to drugs, and also when they have a disease, the so-called same disease, the disease behaves differently. And then we realized something that we should have realized maybe 200 years ago, that we are different from one another. There are not two people on the face of Earth that are identical. You may raise your hand and tell me, oh, you are wrong. Identical twins are identical. And the answer is no. Even identical twins are not identical because epigenetically they are different. So there are changes that occurs in the genome after we are born, methylation of DNA, methylations of histones. I don't want to go into it. So there are not two people that are identical. We are men and women, we are fat and thin, we are tall and low, we are living in different countries, eating different diets, and mostly inherited different genetic repertoire from our parents. Therefore, there is no wonder that we needed something else, and the something else came from this vision, that let's say that you have a group of people that is diagnosed in the same very day with the same disease, and the disease is more or less at the same stage. Let's take women with breast cancer, men with prostate cancer. So you have 100 people that were diagnosed in the same clinic in the same day. And then you give them the best treatment and you let them go. And you realize, and we knew it for years, that after a few years, some of them unfortunately died. The blue one and the orange one died. The problem is that we were blind to the color initially. We thought that they're all the same. But basically they were colored differently already on day one, but we did not know about the coloring. And the green one were cured. Well, it's not in every disease. Some diseases everybody cured. Some diseases everybody dies. Brain cancer, for example, and so on. But on the average, that's what we saw. And then we realized that the models are not serving us well. and we need another model. And the other model is us, the human being. Well, we are not rabbits. We are not living in cages in the laboratory. So we needed a different approach. And the different approach came technologically, and that's the sequencing of the DNA, the Human Genome Project. It started already in the early 90s. It was an initiative in the United States, but then it spread to sequence the human genome. There were already chemical ways to sequence the DNA, but it turned out to be awfully complicated, awfully long, and awfully expensive. And the first human genome took 7 years to sequence, 7 years, from 93 to 2000, and cost about $800 million. So merely in 2000, 22 years ago, people thought that this is going to be useless. We shall not be able to use it on a daily basis in every people, in every person. But technology has come to our help, and it's combined technology, it's computer sciences, and it's changing the sequencing from a chemical to electric. I will not go into the details of it. All in all, nowadays, now in April of 2022, we are able to sequence a whole human genome in less than a day for about $10,000. It's still a long time, not very long, but it's still expensive, but it's coming down. And it's coming down very quickly, and hopefully within no time, it will be kind of a routine hospital testing. And that really opened the way, and it also pushed other technologies. It pushed other technologies because diseases are not coming because of DNA. The DNA is the basic root of many diseases. But remember, on top of the DNA, there is RNA. And on top of the RNA, there are the proteins. And the diseases are mostly due to problems in proteins, mutation, misfolding, aggregation, and so on. But the DNA gives you the initial information. But all in all, technologies also to look into the RNA and into the proteins developed. And now we have a big umbrella called omics. So we have genomics for DNA. We have transcriptomics for RNA. We have proteomics for analyzing proteins. And we have metabolomics for analyzing lipids, glucose, small molecules, and so on. So basically, we now have at hand, some of the technologies are still under improvement and accuracy and generating appropriate databases, but in general, we shall be able or are able already to profile every person in a very precise chemical manner and to get a picture of the disease in the context of the patient. So we are moving now from what we called pajama treatment. I call it one size fits all. Because remember, beforehand, if we have a breast cancer, it was a breast cancer. A woman went to the bath, she thought that she has a lump in the breast, or she went to periodical examination, or a man complained about difficulties in urination and he was found to have prostate cancer. So we treated them all the same. Surgery, chemotherapy, bombardment with poisons, and irradiation with huge side effects. So it was like one size fits all. Why I called it pajama? Because pajama typically doesn't need any measurements. When you walk and you ask for pajama, the seller in the store will tell you that he has 3 sizes, small, medium, and large. And the rest is for the rubber band to accommodate. But now we are moving to, well, I missed a slide. I want to show you a slide of a tailor in Hong Kong that makes suits. So we are now moving to suit-like medicine that will fit, we are really fitting the treatment to the size, to the genetic repertoire, and to the chemical repertoire of the patient. I want to show you just one example, and that breast cancer, and with that to jump to the last one. I'm okay on time, or Peter? If not, stop me. I'm just don't worry. So you see here 2 biopsies from 2 cancer patients, 2 women. You see on the left side, you see the biopsy. The woman complained, and the doctor came with a needle, and under local anesthesia, took a cylinder, just went in. We are doing it today under imaging. Again, this is interventional imaging. So we are directing the needle to the tumor, and we are taking a tiny small sample, and we are going to the microscope, and we can manipulate the sample also by doing all the analysis that I said. In this example, the sample was manipulated by an antibody. So you see, first of all, you see the difference in the shape. Here is one island, here you see scattered island. Even here you see an island of the tumor that has only 5 cells in it. So you see already a difference. But here you see that it's brown, and here there is no brown. The brown is staining. The 2 tumors were stained with the same brush and with the same antibody, but this one didn't catch the stain, and this one caught the stain. And the stain was for mutated estrogen receptor. Estrogen is one of the woman hormones, the female hormone that is in charge of reproduction. And this woman, the antibody is against a mutated estrogen receptor. Once the estrogen receptor is undergoing mutation, it can lead to cancer, and the antibody recognizes specifically the mutated estrogen receptor. This woman also has an estrogen receptor, but it's normal. So the antibody doesn't recognize it. So this woman, the cancer is coming from mutated estrogen receptor, and therefore she can be treated with a drug called tamoxifen, which is counteracting the activity of the mutated estrogen receptor. This woman, if we give her tamoxifen, it will be waste of money, waste of time, and mostly waste of hope. She will die because it will be like giving her water. She has something else because she has cancer. She might have a mutation in the EGF receptor, and therefore she should be treated with an antibody to remove the EGF receptor, which is called Herceptin. And she has a problem, she might have a problem with the progesterone receptor. Then she should be treated with a drug that neutralizes the mutated estrogen receptor, and so on and so forth. So you see that now we are moving into an era in which there are subtypes of disease. So there is no breast cancer anymore. There is breast cancer A, and breast cancer B, and breast cancer C, and D, and E. And they're all sitting under a description that there is a tumor in the breast, but mechanistically and therapeutically, it's meaningless that there is a tumor in the breast. We need to go into the mechanism and to tailor the treatment exactly to the cause of the disease. Since I want to give you an example, I love to drive. You know, I love to drive. So you can imagine that in the morning, in cold Budapest, in the winter, you cannot turn on your car. Okay, the car doesn't turn on. So this is called a disease. The car cannot be turned on. But the reason for the disease can be different. It can be that you forgot the lights and the battery is empty. It can be that you forgot to put gas and the gas tank is empty. It can be that you somehow rode on an unpaved road and you bumped into your oil tank and the oil leaked out and the cylinders are stuck in the barrel. It can be that in the night you have an old car and the rain penetrated into the engine and wetted the sparks. So you see, there is one disease, but already I enumerated for you 4 reasons. If the battery is okay and you will exchange the battery, the car will still not turn on. You need to go into the reason. So this is kind of a simple analogy to what's going on in medicine. So let's go to the very last part. It also has to do with the adverse side reaction. You know, many drugs have side effects, like you know that there is a rash, that if you take penicillin, you get a rash. But I can tell you that there is much worse than rash. People are dying from side effects. There are anaphylactic shock, and so on and so forth. And it's estimated that about between 1/4 and 16% of the people in American hospitals are dying because of side effects. So why I'm sensitive to penicillin and you are not? Again, because of a change in the DNA. So now we are going to take all the people that have sensitivity to insulin and find why they have it. So I don't have to rely on their memory to tell me whether they are sensitive. I can scan their DNA and find to which drug they are sensitive and to which drug they are not sensitive. So you see that this revolution is going not only for fitting the treatment, but also for avoiding side effects. So what we are basically building now you might ask me, how can it be? So every woman in the world has a different breast cancer. So there will be millions of different breast cancer, and we'll have to develop million drugs? No. The answer is not. What we are doing now, when I say we, it's not me, it's the scientific community via different organizations. We are sequencing thousands and thousands of genomes from each disease. And within this sequencing, let's say 5,000, we are finding groups. So 1,000 women will have breast cancer due to estrogen, 1,000 will have due to progesterone, some 1,000 will have due to the EGF receptor, 1,000 will be triple negative, none of those, but they have cancer, so we'll have to find something. So we are going to build a roadmap of the mutations that are causing a certain disease, and then accordingly develop a drug for each subgroup. So it's not that every woman in the world or every man in the world will have its own private different cancer. This will be nonsense. I mean, this will be impossible to even approach. But we are going to subgroup it using those technologies. So let me really go now to the very last part, and that's the roadblocks. I will not go through all of them. I will talk only on 3. And very briefly. 1, many diseases don't have one mutation. They are multigenic diseases. So it's very difficult for us to know who is the driver and who is the hitchhiker, or maybe the car has several drivers. Mostly psychiatric diseases and metabolic diseases. So finding one mutation will not give us an answer. So that complicates the picture. And we shall need the very heavy statistics to understand who participates, statistics of sequencing of patients. This is one problem. Another problem is the price. The price of medicine is going to skyrocket because now there are very few drugs. Let's say for the heart, there is only 1 or 2 drugs for cholesterol. But if there will be 10 reasons why cholesterol is going high, and there will be 10 different drugs, then the share market of each drug will be 10% of the current share market of statins. So the companies will not only have to develop 9 additional drugs beyond statins, but they have to put $8 billion in each of them. So you can imagine that it is going to be more expensive, which is a problem of accessibility even for people that live in very developed countries like Hungary or Germany or Israel. So, because there is a limit to what the health insurance can cover. And the third issue is bioethics. And bioethics is really a problem because if I have a criminal mind, maybe not nowadays, but in the future when the meaning of the genome will be known, I would have walked into this auditorium at 6 o'clock in the morning with a cotton wool and wipe out all the armchairs with alcohol, clean it, and then let you go in. And then I'll take a picture of you or identify you by your name tag. And no doubt that along the last 45 minutes, you put your hand on the armchair and you left your DNA there. You ask me how? Because the skin is shedding cells all the time. Meaning nothing. You don't even feel it. Then after you leave the hall, I'll come back and with a swab, take all the samples of the DNA here and amplify them by PCR, which is a methodology to amplify the DNA. And then I can call you, and one of you, and tell you, I discovered that you have a gene for I don't know what. And if you don't pay me so much, I'm going to put it on the Facebook, on I don't know where. Well, this is really criminal mind. But think about much more serious issues with the DNA, about privacy. Think about insurance companies that might want to know, even now when I go to an insurance company, they ask me whether I have psychiatric disease in the family, whether I have cancer, whether I have this, and accordingly they do my policy, or how old I am. Because if I'm young, I probably will be healthy for many years, but at my age, they might say, oh, you are going to die soon, so the insurance policy will be high. Think about the government that might want to know, the army that want to take only the best people. Think even about your spouse that might want to know how the children will look like. So, and don't be naive about it. Even now, in modern times, and even in the old days, we are getting married by criteria. You know, forget about blind love. It's blind love in the university. We are marrying people of the same skin color, mostly. We are marrying people of the same education, mostly. I don't believe that a professor in the university will marry an illiterate woman that cannot spell her name, right? In big. We are married within the same religion, more or less, though this is mostly, a lot of it is out now. We are marrying in circles. So why not to marry according to the DNA? What's the heck of adding one more criteria? You know, it looks imaginary to you today, but listen, it's coming. Trust me, it's coming. So the issue of privacy is really going to be very sensitive, and people are talking about it, how to keep the information, because it's going to be known, you know, it's going to be a usual practice in the emergency room. When I will walk in a year to the emergency room with a complaint on chest pain, and they will think of heart attack, they will do ECG, they will take some enzymes, but they will sequence my DNA. And they will come back and say, your cholesterol is okay, but in 10 years you might get Alzheimer's because you have an APOE4 gene, which is mutated. So what do you do with this information? You go to your employer that may fire you. You go to the insurance company that may revoke your policy. You go to your wife. Or you go to your children that might carry the gene themselves. So what do you do with such an information? And I think that the best example is Angelina Jolie, that discovered that her mother died of breast cancer, and her aunt, the sister of the mother, died of ovarian cancer because they both carried a gene with high susceptibility to these diseases, and it's called BRCA1, BRCA1, breast cancer number 1. And she suspected that she might carry the gene also. And she was tested and found positive. And what she did, she removed both her breast and her ovaries to remove a ticking bomb from her body, reducing the risk significantly. But what about the children? She has children, not the adopted one with Brad Pitt, her real ones. So what do you do with the children? So there is an old Jewish say that says, the more you know, the more troubled you are. So it's better to be ignorant, illiterate. If you don't know anything, you don't ask questions. If you know much, you're always bothered. But then what to do next? We don't have to be afraid, at all not. It's always in science that you need to ask questions in order to get an answer. And once we know the question, the answer is coming. So think about CRISPR. CRISPR technology is there to edit genes. So it's not in use yet, it's in very limited use, but we are now using all kinds of genetic engineering, as I told you at the beginning of my talk, in order to treat diseases. Spinal muscular atrophy, it's a degenerative disease of which children are dying because they are suffering from paralysis of their muscles, especially of the chest muscles, the breathing muscles, and we are now able to stop the deterioration of the disease by correcting the gene, and so on and so forth. So I think that the future is bright. Personalized medicine is going to be very accurate with minor side effects because it's going to be target-oriented, but it has other P's in it, if you remember. It will be predictive because if I sequence my genes, I can predict the future. If I can predict the future, I may be able to preventive. So it will be preventive, and mostly it will be also participatory. Because what is participatory? The patient himself or herself will need to take part to participate in the decision-making process. Angelina Jolie certainly had to participate in the decision to remove her breast. This is not an easy decision. It's an awfully difficult one. So we shall not be able anymore, for those of you who are in medical school now, or physicians, I remember myself as a young medical student and as a practicing physician, medicine was the profession of God. Doctors were God. Trust me, I'm your doctor. Don't come to me with your stupid questions. Now the patients are taking part in the decision-making process, because the decisions are much more complicated and the knowledge of the people is much broader. Remember, we have social networks, there is Wikipedia, there is Facebook, there are groups, people are asking, they have questions, and those questions, so the doctor takes a side role. The doctor can consult only from his professional knowledge, but the role of the doctor has clearly changed in a big way due to this revolution. So thank you very much for your attention, and I'll end up here.
Thank you very much for this really fascinating presentations. Please, students, the stage is yours, and any questions you have, please raise your hands.
Thank you for your really interesting lecture. And I would like to ask you about what do you think about the role in personalized medicine, so the role of the human microbiome. Because you talked a lot about the human genome, and of course we have lots of bacteria and other organisms in our body. And how do you see the future of the microbiome research?
Yeah, it's a very interesting question about the role of the microbiome. As you know, we have very good neighbors living with us. Actually, between 10 and 100-fold more than the number of our cells. The number of bacteria in our gut is 10 to 100-fold greater than the number of our cells. And the microbiome appears to be playing an important role, though it's still, in a way, a buzzword. You know, people are working by fashion, so people are trying to promote what they have. But it's clear that the microbiome is very different for every one of us. And changing the microbiome has proved to be right in several diseases. And it looks like, again, the microbiome is indeed in an interplay with the genome and develops according to the genome. And therefore, of course, it depends on the diet and so on and so forth, but also on the genome. And there are two diseases in which there are reports about changing the microbiome. One is called Clostridium difficile. It's an infectious disease. The people are dying, mostly old people, they are dying if they have it. It's an infection with a bacteria. And what the treatment is to treat them with feces of healthy people. Well, we have to go down a little bit. It's not that we are going to eat to feed them with feces. But what we do, we take the feces of healthy patients, we dry it, we go into treatment, we put it in capsules and we put it via the anus. But beforehand, we sterilize their own microbiome by heavy antibiotics and washing, and we let the bacteria that we put into the dried feces to populate, and they are cured. Another one is very interesting, and it's melanoma, malignant melanoma. It's a skin cancer, very aggressive skin cancer. It was a science paper a year ago, and it turned out that some of the patients don't react well to the immune therapy, to the antibodies, to PD-L1 and CTLA4. And once the microbiome was changed with the healthy one, the reaction improved dramatically. The problem is that this whole microbiome is still under a fog because there are so many bacteria, different ones, I'm not talking about the number, and they secrete so many compounds that we still don't understand which is the compound or the compounds that are making the magic. So it's still a profession or an area of research in progress. But there is no doubt that it will play an important role. And as you see, drugs are being developed well. And the FDA, the American FDA, is still afraid that what is a healthy person? I'm healthy now, but maybe I'm carrying some viruses to hepatitis. So then I infect the patient. So how we do quality control on feces? So therefore, we need to understand the compounds that are coming out and to purify them, and instead of giving bacteria, to give the relevant, because at the end of the day, it's a compound that makes the activity, it's not the bacteria. It's something that is secreted by the bacteria. But it's a very fascinating field, no doubt.
Thank you. Questions?
Thank you. My question is that you spoke about the new role of doctors will face in the near future, that they will be just consultants. Is this, in your opinion, good? After a lot of study and research, they will be just a second place, because in the social media and on the internet and other forums there are a lot of misinformation, and it is good for the patient, and the doctor community, the community will face this problem in the future.
Well, the information in the social media is certainly not reliable to the extent that you can use it as a professional advice. I would never go to Facebook to find a treatment for my disease. I will go to a professional doctor. But there is still a lot of valid information, and people need to filter it out. I think that the worst example that I can bring you is the anti-vaccination movement with COVID-19, that people, came with all kind of stupidities that, if you are vaccinated, it will stop the fertility of women, and it will do this, and it will do this. This is, of course, all nonsense. These people never heard of messenger RNA. So they read, you cannot become a doctor by getting education from Facebook or from Twitter. The place to learn medicine is in the university, in the medical school, not in Twitter. Twitter is not a university, and Wikipedia neither. So we have to be, once you are using social media, people need to use their intelligence too. Not to be believers and not to believe in anything, but rather to be judgmental about what they are being told, to look for the real literature, to the scientific literature, and so on and so forth. Indeed, I admit, it's confusing, it's very confusing. So at the end of the day, you need professional advice. There is no doubt about it. But you can come up with questions, and you said, I read it, and the doctor or the professional will tell you, yes, there is something in it, but there is more information, or what you read is nonsense, or whatever it is. But I think that the patient of today is much more knowledgeable than the patient 30 years ago. No doubt about it.
Thank you. Questions?
You have mentioned that there are different directions of medicine and modern technology nowadays, and I would like to ask that what do you think, which of these fields will improve in the near future the most, and why?
Well, it's hard to measure rates of progress. Technology is moving very fast, but at the end of the day, we need to solve biological mechanisms. So if we shall not understand what's going on in Alzheimer's, what is memory at all? I mean, we don't understand what is memory. If somebody will tell me, your mother, all of a sudden I see a picture, and I feel the smells of home, and where do they come from? And what is aberrated during Alzheimer's? So I think that technology, with all admiration that we pay it, like the cellular phones and whatever, is extremely primitive relative to the complexity of biological questions. So I think that, therefore, biology needs, there are no jumps in biology. We cannot, even if you put on the table $1 billion and you tell people, solve me the secret of cancer in a year, I give you all the money you need, it will not be solved. You cannot jump. You need to go through steps and to understand cell division, aberrations, genome stability, apoptosis, DNA damage response. There are so many mechanisms around cancer that need to be solved in order to get to the question itself. And there is no way to jump over. So therefore, elucidation of biological processes, in my opinion, is much slower than technology. But they are both moving. I hope I answered your question.
My question is about genetic discrimination and selection. When we figured out that when relatives make children, they often end up with some terrible disabilities. And now I think everybody in this room has a very strong opinion on whether relatives should have children together or not. Now, the time will come, as you said, that when we realize that some genetic models, some genetic pictures should not come together for the betterment of the child. When we figure this out, who should make the decision whether someone should get married or not? Is it going to be the doctors who will be leading the new reproductive culture? Or should we take a sidestep to other opinion leaders? And my second question is, if it is up to us to
Let's
protect...
start with the first one. It's awfully complicated, even the first one.
But maybe the second one is a little bit easier. If it is us who gets to decide, how should we organize among ourselves to have a consistent answer to this question?
Yeah. It's awfully complicated issue, and time will come that we'll need to answer it. I mean, not to answer who will get married and who will not get married. I don't believe that a democratic, normal society will ever go there, especially in the extreme cases, you know, of people that are completely mentally retarded, that you see something. But there will be certainly a screening, you know, and it will come out of maybe of the will of the people to screen themselves, and mostly for screening of embryos. Now you're able, you know, what's happening now in IVF, in vitro fertilization, okay? So let's say that there are women that don't want to have children at a certain stage, okay? And they want to develop their career. Everything is fine. And they want to postpone it or to leave the opportunity for the future. They didn't make any decision yet. So what they do, they are freezing fertilized eggs, either with any spouse that they choose. And in the future, one day, they decide to sew one of those and to get it implanted either in the original mother or in a surrogate mother, doesn't matter. It just shows you, by the way, as I speak, that the term family or living together or love or whatever is becoming completely separated from having children, from having a family, a big family. It's completely separated. Until, I would say, 50 years ago, the tradition was that in order to have a family, you need to get married, and there was children, and they went to school, and so on and so forth. Now it's becoming separated. It's a separate issue. You know, there are many women that want to have children and they don't get married out of will, out of fate, out of whatever. So let's say that this woman now has 15 embryos frozen in liquid nitrogen somewhere. Now she has the choice to select them. And she can select them based on several criteria. Sex, if she wants a daughter or a male. When my mother got pregnant in 47, she had no clue what's going to be born. Everything, there was no even x-ray. You know, somebody was born, that's it. 9 months, she went to the hospital, that's it. No, nothing. Absolutely nothing. And no screening of organs for defects, no nothing, really zero. So this woman that has 50 potential children frozen in liquid nitrogen, listen to the language even, how foreign it is to our parents. She can choose the sex, she can screen for diseases, for mutations, she might ask to correct the mutation, and so on. I didn't go, it's still there, I didn't go to the rest of my talk, I just want to show one slide. How many of you are medical students or doctors? Okay. You know, if you think about medicine, even for the non-doctors among you, medicine is standing on 3 pillars, the 3 real pillars. Patient, disease, right? The patient gets disease, and treatment. These are the 3 main pillars of medicine. They're all going to change. They're all going to change, and I didn't edit, I don't know. Okay, I probably left it out. The patient might be very different. The patient might be the embryo in the liquid nitrogen, the 2 cells or 4 cells, or the single fused egg with a sperm that is now being screened for the DNA. This might be the patient, and I might be able to correct it by CRISPR technology. Remember the stupid experiment that was done by the Chinese guy in Shenzhen Jiankui He, who reported it in the CRISPR meeting 4 years ago in Hong Kong. He's now in prison. He's going to get released. He changed the embryos and removed from them the AIDS virus receptor, the CCR4X, in order to prevent that they will catch AIDS while traversing the vaginal canal of the mother that got AIDS. Of course, it was stupid from any reason, and it was not successful. But the disease will become different because these embryos don't have a disease. But nevertheless, the disease is treated at the patient level, which is an embryo. So we are going to change everything. I think that your question goes well beyond to morality about forbidding people from getting married. I don't want to go into it. I'm not a philosopher. I'm not in the field. But yes, we are certainly scientifically getting there. No doubt about it.
Louder a little bit. Yes, you can go.
All right. So you have said a lot of important information about drugs, but my question is about what's your opinion about homeopathic therapies or medicines? Are they completely useless? Should customers use them?
Listen, people should use whatever they think they benefit from. I'm a scientist, so I believe only in what I see, and what I read is scientifically have grounds. But it's true that the human being is much more complex than we think it is. It's not black and white. People belief is helping, people are religious, they believe that God might help them, and so on and so forth. In my opinion, as a scientist and as a physician, whatever you are bringing to the use of the mass should be proven scientifically. It should act. It cannot be serendipity. And so it's okay. The only danger in homeopathy or Chinese medicine or magicians doesn't matter, is that it's coming instead of conventional medicine. So if people have cancer and they want to go to needle therapy, I most honestly don't believe that needle therapy will take the tumor away. It will not. So we should be very careful about it. You can use it on top of, you can use it on diseases that are not really dangerous. If you have headache or migraine, or your husband makes you nervous, or I don't know what, then, you can do a lot of things. But for real diseases, if you have a heart attack, and you have an arrhythmia, it's better to go to the hospital rather than to take some herb or some I don't know what. So I think that it's a balance. I'm not against it, but I think that it should be used within the appropriate personal context and according to and after ruling out a real disease that can be cured or treated effectively otherwise.
Thank you. Last question.
Thank you very much for your fascinating topic and lecture. So actually, I got a big picture of what's happening in biomedicine and drug innovation. So I just have two questions. One is, you were telling me we can predict the future of disease based on the science that we are using now. So my question is, how are we going to predict the future based on the current knowledge of science? And so what is your thought about this? For example, back then, I was reading your history, and basically in 1917, you were initiated or innovated the ubiquitin. You were also called APF1, but back then, around 2000, it turned out it was identical to ubiquitin. So what if in the future, the current knowledge turned into totally kind of different prediction or kind of mess up? So what is your thought about this? And especially it's sensitive for the genomic studies, I think.
It's very easy to predict the past. Predicting the future is very difficult, but we can see trends. And I think that we should really, science is there, and it's becoming very, very strong. And what helps science make a huge leap advance is communication. Think about the internet. Think even about the Zoom. You know, unfortunately, we got the Zoom under unexpected circumstances, but you know, now I'm able to talk to audiences simultaneously all over the world in no time. I can talk to the Chinese in the morning, to the Americans in the evening, and to the Europeans in noontime. So the communication is, and our accessibility to databases, to the literature, is amazing. So these are all recent developments. And there are very talented people all over the world. And I think that I try to really delineate briefly what's going to happen in medicine, and that's much more accurate diseases and mostly the ability to prevent them, knowing ahead of time that they are going to develop, because it's much better to prevent a disease than to get it there and to treat it. So, of course, people are talking about quantum computing, which will be zillion times faster than current computing. People are talking about AI, which is still a buzzword, but we are using it. I'm using it myself in the laboratory in order to analyze slides to discover things that are not clear to the pathologist's eye, because the AI is blind to any instruction. It looks at things and it discovered all kinds of characteristics that you never thought will be relevant by feeding it with huge amount of data. So we are looking at some cancer bone marrow biopsies, and we are discovering very interesting characteristics. So AI probably is going to play a major role that is also going to affect medicine. And, you know, but the problems never stop coming, because with development we are also somehow committing suicide. Think about climate change, emission of greenhouse gases. So the world is really warming up. So new problems are on the table as we are moving that need to be solved. So, and remember also what really bothers me as a human being, that a large percent of the population in the world doesn't have access to all what we are talking about. You know, poverty and famine and drought are affecting billions of people worldwide. There are very few, or relatively, not very few, few relatively that are enjoying what we are talking about. The world has about 9 billion people right now, 8 billion people. So think about Europe. What is Europe? A few hundred millions. America is another 300 million. Canada, Australia, Japan. We are talking maybe 1.5 billion to 2 billion people that have access to all what we are talking about. And the rest of the world, even in India, Africa, completely decimated. They don't know what we are talking about, and all these achievements will never come there. Think about vaccination to COVID-19. Some countries in Africa never heard about it, or 10% of them got the first shot, which was for nothing. So we are really in a humanitarian problem. So, you know, it's not only, the issue is not only to solve complicated problems of the brain. We have 7 or 6 billion people in the world that don't have flowing water in their homes. So this is a simple problem to solve, but nevertheless, it's not there. So if you ask me, of course, because I'm a scientist, I want to see Alzheimer's solved and cancer being removed from our table. But on the other hand, as a humanitarian, I think a lot about equality, and it looks that we are going nowhere with this one. So you see, we are living in a very complex world. The issues are not just scientific. They are political, they are national, they are religious, they are much more complicated than we think they are. Think about the war that is going on the east side of Hungary now. Just, you know, 2 hours drive from here. Think about the Ukrainians, think about suffering people. Amazing, really amazing.
So,
thank you very much.
So thank you very much, Aaron, again, and your really fascinating presentation. And of course, besides some water, you definitely deserved the medal and to commemorate your coming to Szeged. And thank you for your really very valuable time. And we would like to give you the regular certificate and the medal.